Our next review topic for our prerequisites unit is radicals. Again, I'm going to let you look over all of these properties. Some of them we'll use in this video. Some of them we'll see in a later video. We're not going to be using all of these necessarily today. A little bit of vocab around radicals. Of course, you're familiar with the radical sign. That's the piece that looks like a little check mark. The index tells you which root you're taking. You're most familiar with square roots, and that's if the index isn't there, it's assumed to be a square root. Otherwise, you'll see a number, a cube root, a fourth root, etc. And the value that is under the radical sign is called the radicand. First, we're going to review how to simplify radicals. The goal of simplifying radicals is to pull out any perfect square factors, leaving only factors without perfect squares under the radical. I'm going to show all my steps initially, and then eventually I'm going to kind of take those away and simplify it a little bit faster as you remember how to get these simplified. Your goal is to find, as I said, perfect square factors of the number under the radical, or perfect square factors of the radicand. If you know off the top of your head that 16 goes into 80, you can split it up as 16 times 5. If you do not know off the top of your head that 16 is a factor of 80, you can create a factor tree until you find perfect square factors. You can choose any two numbers to start with for your factor tree, because eventually you'll get down to pairs of numbers that give you a perfect square. Here 4 is a perfect square, and 2 times 2 is a perfect square. So you can still get to 16 as your perfect square factor. One property of radicals is that if you have only multiplication or division under the radical sign, you can split it up into multiple radical signs. The square root of 16 is 4. 5 has no perfect square factor left, so that stays under the radical. Our next example has us multiplying values together. It is helpful to put these together under one radical. Instead of multiplying these together, I'm going to break them up. I know that 6 goes into 18, so I'm going to rewrite 18 as 6 times 3. Of course, 6 squared is a perfect square. The square root of 6 squared is 6, and 3 has no perfect square factor left over. This last example, I'm again going to put them together under one radical. I'm going to put the numbers next to each other, and I'll multiply the variables together. In this case, 16 does not go into 24, but they do have a factor in common. 8 goes into both of them. So I'm going to split up 24 as 8 times 3. 16 is 8 times 2. And then I can reorganize. 8 squared is a perfect square. X squared is a perfect square. And I have 3 times 2, or 6, left over. The square root of 8 squared is 8. The square root of x squared is x. And 6 has no perfect square factor left over. You can divide radicals the same way that you multiply them. Put them together under one radical. 162x to the 5th divided by 2x. 162 divided by 2 is 81. X to the 5th divided by x is x to the 4th. Taking the square root of each piece, we have 9x squared. Again, putting these together under one radical, 54x squared divided by 3x to the negative 1. 54 divided by 3 is 18. Moving that x to the negative 1 up to the numerator gives us an x cubed. And now we'll simplify. The perfect square factor of 18 is 9. The perfect square factor of x cubed is x squared. And we had 2x left over from each of those pieces. So let me explain what I did in case you didn't follow. I'm starting to take out some of my steps. So instead of writing 9 times 2 under one radical, I split them up into two radicals, and x squared times x gives us x cubed. Again, I split them up instead of writing them under one radical and then splitting them up. I put all of the perfect square factors in the first radical, so I can take the square root of 9 and x squared, and 2x does not have any perfect square factors, so that stays under the radical. The last topic of radicals we're going to look at today is adding and subtracting. Adding and subtracting radicals is very similar to adding and subtracting variables. They have to be like terms before you can combine them. Our first example, we have root 6 on both pieces. You can think of that like your variable. 3x plus 5x is 8x. So 3 times the square root of 6 plus 5 times the square root of 6 is 8 times the square root of 6. 6 has no perfect square factors, so we can't simplify that expression any further. Example B, we do not have the same value under the radical, so we cannot subtract these. We'll start by simplifying and then see if we can combine them after that. 48 has a perfect square factor of 16. 48 is 16 times 3. The square root of 16 is 4, and I will multiply that by the 2 that is out front. 3 is left under the radical. 27 has a perfect square factor of 9. 9 times 3. Taking the square root of 9, that comes out from the radical, and 3 is left over. Multiplying our coefficients, I get 8 root 3 minus 9 root 3, which leaves me with a negative square root of 3. Our final example, we'll take a look at that one more time. We saw the square root of 80 simplified earlier, 16 times 5. 45 is 9 times 5. And the perfect square factor of 50 is 25. That's 25 times 2. Taking the square root of 16, which is 4, and multiplying it by the 3, I get 12 times the square root of 5. Taking the square root of 9, I get 3. Multiplying by the 7, I get 21 times the square root of 5. Taking the square root of 25, I get 5. Multiplying by the 5, I get 25 times the square root of 2. Notice we have two like terms in this one, and that third term is unlike. So this would be like 12x plus 21x minus 25y. We cannot combine them all together, so I will add my like terms to get 33 times the square root of 5, and that 25 times the square root of 2 is on its own. Here are your 2 you try questions. Please come to class with these attempted so we can start our time productively together.